In this video, I am going to talk about how to calculate the number of group homomorphisms from a finite group G to finite group H. Okay, so in most of the exams like JAM, NET, GATE, also in the subjective question paper, this kind of question usually comes that compute number of group homomorphisms from some group to some group, right? So you can find some formula, okay, for some particular group, but in general it is quite difficult to count. Okay, so I just want to tell that the exact theory, that how we can think that what kind of group homomorphism can it be from group G to H, or how a group homomorphism comes from here. So it is basically an application of first isomorphism theorem, and we have to do that. Okay, so let's start. So some steps. Okay, so first you need to know all possible normal subgroups of G, okay, and how the quotients looks like. How the quotients so what I'm saying that let subgroup, you need to understand G mod K, okay, whether this is isomorphic to your known group or not. Say suppose G mod K, order of G mod K is 4. Okay, so as an example, say 4, then you know that G mod K is isomorphic to Z4 or K4. Now for different group, you need to understand that how it looks like. Okay, what is exactly. So first you need to know all possible normal subgroups of G, and then you have to know that how the quotients of that, if you quotient it by that normal subgroup, how it looks like. Okay, and in the next step is that so usually what we can do, usually it happens that the quotient is usually some known subgroup, so that you know that what the automorphism group is, and then it helps you to compute the exact number of homomorphism. Okay, and the third step is possible subgroups of H. Okay, so you are computing the number of group homomorphisms from G to H. So first you need to know the all possible normal subgroups of G, how the quotient looks like, how the automorphism group of G mod K looks like, and the all possible subgroups of H. Okay, so if you have this information, then you can compute that number of group homomorphisms from Z to H. So at least this theory helps you to compute number of group homomorphism from the standard groups. So standard group means I am talking about K4, Q8, DN, SN, ZN. Okay, so number of group homomorphism from these to that group, it helps you because you know already the what are the normal subgroups looks like, how the quotient looks like, and what are the automorphism group of this known group. Okay, so then you can easily compute say DN to SM, or say Q8 to K4, or K4 to Q8, or K4 to S4, something like that, or Z8 to K4, anything like that. Okay, and these are the standard groups, and these are the standard question usually asked in most of the exams, that find number of homomorphisms from the standard groups to standard group. Okay, So what is the exact theory? Okay, exact theory behind it. So you know, by first isomorphism theorem, G mod kernel phi is isomorphic to image phi, where phi from G to H is a group homomorphism. So basically our goal is to find the choices of the kernel and the corresponding image so that we can compute. Okay, so what is the exact formula? Okay, or how to compute it? So let K be a normal subgroup of G. Okay, and say G mod K is isomorphic to say P. Okay, okay, then if there is such a homomorphism, if there exists such a homomorphism, then T is a subgroup of H, right? Because image is always a subgroup of the codomain group, right? And again, so you have an isomorphism from G mod K to T, right? So say this is an isomorphism, say I. Now G mod K itself has an automorphism. So for each automorphism, if you composite it with identity map, you will get this I. But if there is some different automorphism of G mod K, then this composition map will be different. What I want to say you have already, so fix a K normal in G, look at G mod K and say it is isomorphic to T, which is a subgroup of H. Okay, and say this isomorphism is I. Okay, pick one isomorphism, it is I. Now we have already G mod K to G mod K, this is identity map, identity. Then if you compose it, you will get I. But if G mod K has a different automorphism, say G mod K to G mod K, there is a different automorphism, say psi. Then if you compose it with I, then this composition, I compose psi, must be different from I. So this gives you a different isomorphism from G mod K to T, and that gives you a different homomorphism, right? Because under this map is completely different. So for exactly one fixed automorphism, you will have a different homomorphism so that the corresponding quotient is isomorphic to T, and this homomorphism depends on the number of automorphisms of G mod K, right? Because these maps comes from number of automorphisms. So if you permute it, one kind of permutation and one kind of automorphism of G mod K, then if you compose it, you will get the same, right? You will get different. So for a fixed K and a T, for a fixed K and a fixed T, number of homomorphisms you will get cardinality of out of G mod K, right? Now T can be different, right? Because H may have different subgroup, both are isomorphic, right? So you are fixing one T, right, where T is a subgroup of H, but it may have that T1 and T2 to different subgroup, and that both are isomorphic to G mod K. Then you will get different homomorphism mapping G mod K to that subgroup, right? So that's why you need to count the number of T type subgroup inside H. Okay, so that's why you need to compute number of T type subgroup. T type means isomorphic to T subgroup of H. Say it in. Then number of group homomorphism phi having kernel K, kernel equal to K, is order of automorphism of G mod K times number of T type subgroup of H. Okay. Now find all possible numbers of normal subgroups. Say it is K1, K2 up to Kr, the number of group homomorphism. So number of group homomorphism that has kernel K1 is automorphism group of G mod K, order of automorphism group of G mod K, times number of G mod K isomorphic subgroups inside H, which is T type subgroup, right? Similarly for K2 it is true, similarly for K3 it is true, similarly for Kr it is true. So number of group homomorphism will be summation I equal to 1 to R order of automorphism G mod Ki times, if T is, say, G mod Ki is isomorphic to Ti, number of Ti type subgroup in H. Okay. So the important thing is here, you have to find all possible normal subgroup. You need to see what are the quotient looks like, and then you have to compute the how many that same kind of quotient sub. The quotient, say G mod K, is isomorphic to must be image. So image must be a subgroup of the codomain group. You need to compute that how many that same kind of subgroup is there. Because for different subgroup you will get different morphism, but kernel is fixed, right? Because so it may happen that K is fixed, kernel is fixed, but the image may be different. This is isomorphic, but it may be different, right? It depends on how you map, how you define the map. So for a fixed kernel, image may be different. So that's why we need to multiply this factor, okay? And also we first fix a subgroup K, which is normal already. So that is a possible kernel for, that's a possible choice of kernel in our case, right? That's why, and for each automorphism of this G mod K, we will have a different homomorphism that we already see. Here is already an isomorphism. See, if we compose it with a different automorphism, this gives a different isomorphism, right? Now we know that we don't know what is the exact isomorphism. We are taking the all possible combination, all possibility, right? That's why there is all possibility. So to get all possibility, we need to multiply with the automorphism, order of the automorphism group, because each factor comes from the automorphism, one automorphism, by composing with another automorphism, okay? That's why we get this factor, and for the image we get this factor, okay? So ultimately the counting of homomorphism depends only on the choice of kernel phi and image phi. So we need to find all possible choice of kernel and all possible choice of image. If we get that, then finally we will get the answer. So this is the answer. Now you can apply this. Okay. Now exercise. You can do the same proof and prove that you can prove. Also, you can find you can compute the number of group homomorphism from K4 to Q8, S4 to S3, Sn to Sm, anything like that. Because you already know what are the Dn to something, what are the normal subgroups are, what are the subgroups looks like, and you can compute by this formula. Okay. So it is a very important thing. So if you have any doubt, you may have some doubt in this discussion. So please comment. Okay. If you have any doubt, please comment. I will definitely reply. And also try to compute by hand and try to check that whether your answer is correct or not. Okay, this is the exact theory. So everything depends on the first isomorphism theorem, and you need to find the possible choice of kernel as well as possible choice of image. That's all. Okay.